So that's our job, to do that integral. Suppose I now, Sebastian, this is in the spirit of your talk, I say, okay, it's great. You've given it to me in discrete time. I can write an algorithm. But I want to get an idea of what the structure is underneath. So I'm going to go to continuous time so that I can write everything I need to do in terms of differential equations. If you write it in continuous time, then this action is a function of, it's an integral over time over a quantity that in the physics world is called a Lagrangian. To minimize this Lagrangian, which is stated right here, you use a result from classical physics, classical variational calculus, called the Euler-Lagrange equations. Who in this room has never heard of the Euler-Lagrange equations? We're done. The Euler-Lagrange equations, I won't derive for you, but they come with the equation itself plus boundary conditions on the solution that formally come from the integration by parts that you need to derive the Euler-Lagrange equations. The term that you get by integrating by parts is delta x, delta of the state, at the initial time times the derivative of this Lagrangian thing with respect to the velocity. That has to vanish, and exactly the same quantity has to vanish at the final time. This has a fancy name. It's called a canonical momentum. It doesn't matter. This differential equation is what you need to solve. Look here at the right-hand side. Anybody seen that this afternoon before?
X9 minus y.
Yeah. This is the nudging term, not for a first-order differential equation, but appropriate for what the Euler-Lagrange equation is. Once you give me the standard model, this is just arithmetic to give you this differential equation. What does it mean? This balances the uncertainty in your knowledge of the measurements against the uncertainty in your knowledge of the model in order to get an extremum, which you can then check actually is a minimum of the action. So that's the real equation. Look what's different. This is the original equation of motion, which by hand, in our transistor problem, we just set equal to u of t times x minus y. But that's wrong, because we have to include this term as well. And I'm going to show you that that's a real blessing, perhaps at this moment in disguise, but it's a real blessing. Everybody ready? I want to go to the next slide. If you write out this differential equation, what you find is that it's a second-order differential equation. So it's dx squared dt squared. This is the path now in continuous time of all of the state variables. This is the equation that you have to satisfy for that path. The second term involves the Jacobian of the underlying dynamics, df dx, which we've seen before. But the antisymmetric part of it, I call that omega. And then the derivative of the rest of it, this is the measurement error, and this is the remainder from the action itself from the f squared term. This is exactly analogous in a funny space of a charged particle moving in a magnetic field and an electric field in d dimensions, driven by information transferred at specific times, tau, by the measurements. This is dx squared dt squared v cross b in d dimensions, not 3 dimensions, And this gradient of this and the gradient and the time gradient of that are what appear as the electric field. This is an inhomogeneous problem with the motion of a charged particle in a specified electric and magnetic field, a nonlinear function of the position. So it's the motion of a charged particle in an inhomogeneous magnetic field driven by the measurements. There's even a gauge condition associated with this. But this differential equation underlies, determines the optimal path given Gaussian errors in the measurement and Gaussian errors in the model. I think, since I don't understand this equation altogether very well yet, that our attention should be focused on learning how to solve this equation for transistors as well as atmospheres. I just throw those two slightly different dimension size problems into the same pot for you. And we probably have a lot to learn, although I can certainly say I haven't learned it yet, from plasma physicists who study the motion of charged particles in complex, inhomogeneous electric and magnetic fields driven by heating in order to build tokamaks, to build fusion devices. This is not something I'm making up, but following from the assumptions of Gaussian errors in models and measurements, this Euler-Lagrange equation is rigorously needs to be solved.
So what you consider was weak constraint for the wall, right? That's what it's called for the street, as far as I can tell.
That's the words that are used, but why is anything weak here?
Well, the weak comes from...
Oh, because we're not imposing the equations of motion precisely.
Exactly, so you allow for
But
formal error.
if I hadn't already done that, I would attribute it to your talk yesterday.
Yeah, but
That's right. But I'm going to show you how to use the structure of weak constraint 4D-FAR in a way that is different from usual, that will allow us, in the numerical case, not the differential equation case, to, when I say numerical, I mean discrete time case, to get a picture of what's going on.
right. So you're saying basically the minimizer of weak constraint for gives rise to the equation you written up there.
Exactly. That's exactly what I'm saying. And I can...
The boundary conditions.
Gives the boundary conditions, and in fact, let me say one further thing, because this is actually kind of interesting, although I truly don't know the depths of the properties of this equation. Suppose you make the error in the model smaller and smaller and smaller. That means you increase the precision of the model more and more and more. And that means the scale of the inverse covariance matrix gets bigger and bigger and bigger and bigger. The precision gets bigger and bigger and bigger. In the formal limit, and I think you have to approach that limit very carefully, what you have here is a small perturbation due to the observations of a homogeneous but nonlinear ordinary differential equation with precise boundary conditions. It's a two-point boundary value problem and a nonlinear problem. And quite typically, what I've just described has only selected solutions for the parameters in the problem. Parameters in the problem enter in the model, and they enter in the accuracy of the measurements versus the precision of the model. So I think that an interesting way to approach finding the path that corresponds to the best approximation in the Laplace sense of the integrals you need to do comes from solving something very close to that two-point boundary value problem.
Actually, you're not doing weak constraint for the you're doing different minimization. It's not weak constraint for the
Oh, the action's the same.
No.
No?
Is it?
Yeah, it's quadratic. Never mind a measurement function. You can put that in and make it more complicated. This is the state variables x minus the measurement squared with some weight, and x dot minus f squared with some weight.
Well, maybe we want to talk about it later. I sense there are some scaling issues there. It's a little bit different.
Oh, it's true. When you go from discrete time to the continuous time, the dimensions of the various terms change by factors of delta t.
Yeah, but there are different limits, and I think you're taking a different limit. But anyway, it's
Okay. Could be. All right. I'm putting this on the board because when you define it to your satisfaction, you're ending up with a charged particle moving in an inhomogeneous.
Yeah, that's your scaling limit. That's
Yeah.
why, I mean, anyway, maybe we should discuss it later.
Okay.
It's a different scaling limit.
All right.
Henry?
Dan.
So you say that this is a problem that is incomplete except in special cases.
I haven't told. That's correct.
And then everything you're interested in seems to be a special case. So
Well, I'm saying that the general form of the action, given the separation between model operations and measurement operations, leads you to this in the action. I'll show you the special case in a moment. All right, I'm now going to go back to Laplace's method in discrete time. And here's the special case. In the limit r goes to Rf goes to infinity, the precision of the model is perfect. This term becomes a delta function. All the nonlinearity that makes the minimization of the action complicated lies in here. Suppose you go to the other limit and you make the model completely imprecise and you go to Rf equals 0. Then you have to minimize this. That's no big deal. That says x equal y in the variables that you measured. And it's very degenerate because it is completely independent of the variables you didn't measure. So our procedure, which we call variational assimilation, does the following. It starts off at Rf equals 0 and determines a set of action levels that depend upon your state variables being those of your measurements, plus random choices for all the other variables because it's independent of that. And then it makes Rf very small, 10 to the minus 4, 10 to the minus 5 in some units. So this is a small perturbation of that. It then does the optimization calculation using whatever minimization program you want, starting with the solution to the previous problem. And then it turns Rf from 10 to the minus 5 to 10 to the minus 4 and does the optimization again for a little bit bigger Rf, a little bit more nonlinearity. And the goal is to stay in the global minimum of the problem as you systematically increase Rf. If you increase it too fast, you'll jump out into the other minima. And I want to show you the result of that kind of calculation for the Lorentz 96 model, which you've heard about and worked on, for Hodgkin-Huxley model. I think that's all I brought along.